Hi folks, we are on the Unit 2 Day 7 lesson, and in this lesson we're going to take a look at the cross product. So if you remember from earlier in the unit, we talked about how there are two different kinds of multiplication of two vectors. The dot product, which is also called the scalar product because it gives a scalar as an answer, and the cross product that's sometimes called the vector product because the result of this one will be a vector. And I think that this is exactly what I just said. So again, making sure you realize that if you have a dot b, you get a scalar, or if you have a cross b, you get a vector. You also kind of want to take a look maybe back at the first day of dot product and review the notation. It is really important. Remember with real numbers how sometimes we just put a dot, sometimes we put an X, and they all mean multiplication. With dot product and cross product, they're very different things. So you have to be very careful here with the notation between those. Another note, we're never going to say U times V because that's not times or multiplying isn't actually an operation that we have, and you have to be very specific and very clear on whether you want to do dot product or cross product. So we would never ever say U times V with vectors. We say U dot V or U cross V to distinguish between those two types of vector multiplication. So the cross product of U and V is defined as a vector that's perpendicular to both of the vectors that you're doing the cross product of. So I probably should have changed this to A and B, but you can see what this means. If you have two vectors here, the cross product is the vector that comes out perpendicular to both of them, and it's going to actually have a magnitude of the area of this parallelogram, which we're going to get into more in the next lesson. But just it is a little bit arbitrary what the magnitude is, but it does end up being the magnitude of the area of that parallelogram. But it's very, very important, especially in Unit 3 when we're looking at equations of lines and planes, to be able to find things that are perpendicular, to be able to define things that can identify perpendicular vectors. Another important thing here is that the cross product is only defined in R3, right? If you had we could do dot product in R2 or R3, but in R2, if you had two vectors drawn on a flat surface, you can't draw a third vector that's perpendicular to both of those without coming kind of out of the page. So we need this third dimension to be able to get that third vector to be perpendicular to the first two. That's not something that's possible to do in just two dimensions. So we are going to derive the dot product, or the cross product, pardon me. It does get pretty messy, but I think it's important for you to see where these calculations come from, where things are coming from, and how we can figure out equations for these kinds of concepts. So we're going to use all math that you know how to do, and all things that you've already learned, but I think that it's a worthwhile exercise to just kind of go through and see. You wouldn't likely be able to derive this, most of you, but to be able to follow it and see the reasoning of where did this formula come from, because the formula is a bit of a mess. So I think kind of seeing the reasoning behind it makes people understand it a little bit better. So if we know that A cross B gives us a vector that's perpendicular to both of those. Earlier in this unit, I said that if you saw the word perpendicular, I wanted you to immediately think one important thing with vectors, and that was the dot product is 0. That's so important. Whenever we hear perpendicular, two vectors are perpendicular, their dot product is 0. So, and I know it seems a little bit counterintuitive to be using dot product if what we actually want to figure out is the cross product, but if V equals A cross B, then we know V is going to be perpendicular to A and V is also going to be perpendicular to B. So I'm going to use that information here. V is perpendicular to A and V is perpendicular to B. And the important information that we know two vectors being perpendicular means that they have a dot product that equals 0. So I'm going to just kind of in alphabetical order here. A dot V equals 0 and B dot V equals 0. I have written A and B and V into component form, and I've just said A1, A2, A3, B1, B2, B3, and the resulting vector that is the cross product is X, Y, Z. So what we really want to figure out is how can we find this cross product, the X and the Y and the Z components of the cross product, given these two. So we want to end up with some kind of equation like X equals Y equals Z equals, because that is the cross product. And we want that somehow in terms of the components of vector A and B. That's kind of our goal. So we want to figure out something like this, and it is going to be a bit of a slog, but we can do it. So if we know that A dot V equals 0, that would be A1X plus A2Y plus A3Z would equal 0. And similarly, B dot V equals 0 would give us B1X plus B2Y plus B3Z equals 0. So those two equations are really what we know. And I want to figure out how to kind of solve these, rearrange these for X equals Y equals Z equals. And what you may be thinking right now is that I have 3 variables, X, Y, and Z, but I only have 2 different equations. So that's actually not possible to solve specifically. And really, we know that there would actually be an infinite number of vectors that are perpendicular to both A and B. But all of those vectors are going to be scalar multiples of my V. All of the vectors that are perpendicular to both of these will be scalar multiples of each other. So for instance, I'm going to kind of do pen math here. If I have those 2 vectors and I want to find a third vector that's perpendicular to them, I maybe could put that vector, but it also could be a vector twice as long, or it also could be a very short vector, or it also could be a vector going in the other direction. But any vector that's perpendicular to both of these 2 would be a scalar multiple in some direction of this green pen vector. So I'm going to start, actually I'm maybe going to get another piece of paper. So I'm just going to use these equations, and when we're trying to solve for variables given 2 equations, the a common thing that we do is elimination. So I'm going to use elimination to solve for, create an equation by eliminating x. So I'm going to start with a1x plus a2y plus a3z equals 0, and b1x plus b2y plus b3z equals 0. So to do elimination here, I need to multiply to get the same coefficient for both of these. I'm going to multiply this times b1 and this one times a1. And then both of the x variables will have the same coefficient. So this is just like elimination in grade 10, but way more variables and way more messy. So we've got a1 b1x plus a2 b1y plus a3b1z equals 0. And then we have a1b1x plus a1b2y, I have to be careful with all these subscripts, plus a1b3z equals 0. And then I'm going to subtract these. So I'm subtracting these to eliminate the x's. So then I'll have an equation with just y's and z's and all of these a1, b1, a2, b2s. But those we know are going to be actual numbers once we get our equation. So here I'm going to end up subtracting these y coefficients. So I'll have a2b1y, minus a1b2. So that's how many y's I have. And then I'm going to have this many z's minus this many z's. So a3b1z, nope, no z yet. I'm going to collect like terms right in here. a1b3z equals 0. So that gives me an equation here. I'm going to bring one of these to the other side. I'm just going to isolate the y by swapping this to the other side, and then we're going to divide them out. So when I move this to the other side, I'm going to multiply it by -1. So here I've got a3b1 minus a1b3z equals, and so I'm multiplying by a -1 there when I am going to be bringing this over, but I'm just to save myself some space. So this one will be negative and this one will be positive, and I'm going to swap the order. So just kind of pay close attention there. I'll get a1b2 minus a2b1 for my y's. And then I'm going to set up a ratio of just dividing both sides by these big coefficients. So I have, I almost want this to kind of look like a sine law, like something, a variable over something equals a variable over something. So I'm dividing both sides by both of these brackets and they will cancel out. So I'm going to get z over a1 b2 minus a2b1 equals y over a3b1 minus a1b3. So just to put a note here, I divided both sides by both brackets. So that gives me this kind of stopping point, I am going to stop there. And we're going to have to redo a sort of similar thing to eliminate a different variable, because this doesn't have anything to do with the x's yet. And fairly arbitrarily, I'm going to say that we will eliminate z. It doesn't actually really matter which one you did, y or z. But I'm going to go back to my original equations and try and get the same for coefficient for the z's and subtract, and then I'll have an equation with just x's and y's. So we had an equation with just y's and z's. Now we'll have an equation with just x's and y's and see if we're able to put those together. So I'm going to start again from a1x plus a2y plus a3z equals 0, and b1x plus b2y plus b3z equals 0. So I am going to take the first equation, because I want to get the same coefficient for the z's, and multiply by b3, and take the second equation and multiply by a3. And then I will have same equations for each of those so that I can subtract and eliminate a variable. So my x's here, I've got a1b3x plus a2b3y plus a3b3z equals 0. And then multiplying through by a3 here, I get a3b1x plus a3b2y plus a3b3z equals 0. And this is such a nightmare of all of these little letters. It is pretty easy to make a mistake on these. So I'm going to subtract again, just elimination, so I've got the same thing there. So when I subtract my coefficients here for the x's, I'm going to have a1b3 minus a3b1 x's, and then for the y's, I'll have a2b3 minus a3b2 of y's equals 0, because those z's were eliminated. Now, same thing that I did up here, I'm going to bring this time the x's over to the other side, and that's going to have a factor of -1 in there, which I'm going to do all in one step. This is going to be positive, this will be negative, and I'll just swap their order. So the y piece I'm leaving the same, a2b3 minus a3b2 y equals, now these guys are turning negative, so I'm swapping them around, a3b1 minus a1b3, and that's x's. And then same idea again, very much in parallel to the other example, I'm going to divide both sides by both brackets. And just kind of for space, brackets. I'm not going to show that out because I'm getting to the end of my page. But if this bracket divides down here, and this one is going to divide down there, they would cancel out with themselves. So I will get y over a3b1 minus a1b3 equals x over a2b3 minus a3b2. So that gives me another equation, and there's a really important thing that we want to notice if we look at these two pairs of equations. And hopefully you'll see that this piece with the y is the same as this piece with the y. So this is where I feel like it kind of looks like a like a sine law. Like you've got this equals this and this same thing equals this. So we can say that all three of these things, the ratio with the y, the ratio with the z, and the ratio with the x, are going to be equal to each other. So I'm going to go and write that as x over A2B3 minus A3B2 equals y over, and this is the same in both, A3B1 minus A1B3 equals z over A1B2 minus A2B1. So that doesn't feel like a great formula. It's still really messy. And we don't actually know what these are equal to. We just know that they're equal to each other. So remember how I said that there's actually an infinite number of scalar multiples? We need to just choose one. And let's choose one that makes our math the easiest. So there's an infinite number of vectors perpendicular to A and B. We just need to pick one. And we are fairly arbitrarily, I'm going to say let this equal K, some constant. This ratio is equal to each other. It has to be equal to something. So fairly arbitrarily, but just to make our math easier, we're going to pick one of these infinite number of possibilities, and I'm just going to say let K equals 1, because that's the easiest thing to do. So then each of these ratios equals 1. So I am really squishing this in at the bottom down here. So here I have x over A2B3 minus A3B2 equals 1, which gives me x equals, multiplying this up, A2B3 minus A3B2. So I've got my equation for x. Remember back on this nice page before we saw this mess, we said we want x, y, and z in terms of A1, A2, A3, B1, B2, B3. Now we got x. X is A2 times B3 minus A3 times B2. We're going to do the same for y and z. So y over A3B1 minus A1B3 equals 1. So then y equals A3B1 minus A1B3. And then z over A1B2 minus A2B1 equals 1. We get z equals the stuff on the bottom, A1B2 minus A2B1. This is still not great equations, but I'm going to show you in the next video a much nicer shortcut of how to do them. But there we did get it. So just by setting both of these dot products equal to 0, setting up the equations that resulted from that, doing kind of multiple sets of elimination and rearranging stuff, and a little bit of luck and a little bit of arbitrarily picking one of the infinite possibilities, we did come up with our x, y, and z equations for that cross product in terms of the components of the original vectors. One last thing before we finish. there is something called a right-handed rule. So this is kind of a diagram, or I can just show my own hand under the camera. Because the vector that's perpendicular to the other two vectors could be going in either direction. It's arbitrary. We pick, and the one that we got here by choosing k equals 1, we choose a vector that if you were looking down that vector, so if I had, you have to kind of like make that shape with your hand and pretend that you're like a 6-year-old shooting your brother with your pointer finger. And if you look down from above, like the camera is now, this is the cross product. My thumb is the cross product. It goes in the direction where if you're looking down that vector towards the base, vector u goes counterclockwise to vector v. So this is the cross product, my thumb. Vector u would be my pointer, and vector v would be the other one. So we know it wouldn't be pointing downwards because my thumb doesn't go that way. So you can kind of, this will come more in our discussion when we talk about applications of the cross product. But it just kind of, the way we chose our k value ends up giving us this vector that if you have u going counterclockwise towards v, if that's the way you're looking at it, the u cross v would go up from there.